probably have 3 or 4 long problems or problems in which you would actually have to show me your steps to the solution and come up ultimately with the solution, like the quiz problems that you have had, except that you're going to have more time for each problem on the examination. So I might ask you to take it a little bit further than I asked you on the quiz, right? But let's say problems of the style of the quiz problems. I think that I posted, but I don't know if I did. Someone can tell me. Did I post last year's exams?
Nope.
No? Okay, then I will try to remember to do that, actually post last year's examinations. So that you get some example of what kinds of questions I ask, but the quizzes I think are pretty representative. But there is an aspect to the exams that is not like the quizzes at all. The 5th problem on the quiz will be probably on the exam. 5th problem on the exam will probably be 5 multiple choices. All right? And one of them on last year's examination was this. I actually put 2 problems on last year's electromagnetic theory problem exam that came off of the Physics 2 exam. Honors Physics 2. One of them was from regular Physics 2. And so here's one. I've got 5 charges arranged on the vertices of a hexagon. And there's one that's not there. All right? And let's say they're positive charges with charge plus q, radius r. What's the electric field there? And the answers were 0, 5q over r squared, 6q over r squared, 5q over r, and q over r squared.
So this is the 10th
All right? So those were your choices.
E field?
E field.
No.
At the center.
At the center. All right? And you have 2 approaches to solving this problem. One is really quick, and the other one is not so quick. I'm not going to give you this one again, but I'm looking at it, I'm surprised that I didn't ask you to tell me what direction the field points in as well. And what you can think of this problem as, I want to use it as an example, is this problem with all 6 charges there minus that one, where those 2 have got to be overlapped, so I'll draw a minus charge there. All right? So at that point there, I've got a positive charge and a negative charge sitting on top of one another. You can conceive of it that way, which add up to nothing. All right? The sum of the 6 charges is 0 at the center. The field due to the 6 charges is 0 at the center. And then what's left over is the negative charge that canceled this one here. So the field points that way, and it's the field due to one charge, one negative charge, sitting there. Right? That's a really good trick that is equally useful, probably much more useful, for the other problem that was given on last year's examination, which was this. I have a uniform distribution of charge, spherical uniform distribution of charge, out of which I carve and make
Death Star?
What?
The Death Star?
Yes, okay, it's a Death Star. So over here, I've got charge distributed throughout. Over here, I've got nothing. So I just carve a hole in this distribution of charge. What is the, so then you could ask, what's the electric field at some other point or potential at some point? Right? The easy way to address this problem, let's say I ask you for the electric field over here, is to consider this to be a uniform distribution of charge, which just gives me KQ, which just gives me Q over R squared over here, pointing from the center there, right? And a negative equal density of charge that cancels that out. So I end up adding the field due to, let's call it Q plus the field due to Q minus at their respective locations, right? So this problem, which could be really horrible to solve if you actually had to integrate over all of this distribution without that, right, becomes really easy because it's the field due to this minus the field due to that. Then you're done. Okay? So this idea, the superposition principle, is very useful for solving problems quickly, rather than having to actually do the integers. All right? So I wanted to bring that up because I realized as I was looking over last year's examination that I had two problems on the exam which were made easy by superposition. And although I've used the word, I actually haven't showed you how to solve, hadn't showed you an example of a problem that you might solve using that technique, okay?
Destroyed everyone.
Actually, no. The average on the exam was quite reasonable.
What was the average on these questions, though?
On that question was probably 15%. No. No, if I remember correctly, it's sort of balanced across. It turns out that some students solved it because they had taken astrophysics and learned shell theorem or something like that. The shell theorem, is that what gets applied? Yeah.
And so they actually were able to do the integral.
No. The shell theorem deals with superposition. I'll skip that one.
I remember doing a problem like that.
So the first problem on last year's examination, first exam, was that one. Okay, I lost. It was actually two cylinders, not spheres, cylinders. And by the way, you find out that the electric field in here is constant, pointing in one direction. And the surface charge density on that hole is sigma 0 cosine theta. Yeah.
Go dipoles.
The second problem on last year's examination was, I'm not going to do them, I'm just going to show them, and then if somebody asks a question, I'll answer the question. Was this one a line of charge where the charge density is equal to A plus B Z, so that must be the Z direction, from Z equals 0 to Z equals L. Find the electric field at this point over here, L over 2 off the axis. That one should really only be done by, well, you have a choice, but you can do it by finding the component of the electric field from each little element here and integrating it, or finding the potential and then taking the gradient of the potential. Either one takes about the same amount of work.
Definitely the potential.
What?
Nothing.
Okay. Probably, by the way, you get more partial credit by taking the potential approach, because there are more steps to the potential approach where you could get credit for each step along the path, all right? And then if you make a mistake, then you only lose some small fraction of the points. Whereas if you write down the general equation for the electric field and then make a mistake right away, then you probably lose more points. Yes, Adam?
So for the potential approach, you would do the up boundary case you just.
No, oh, I'm glad you, no. Here's, I would solve this problem. V of x, y, z is equal to the integral of lambda dz over x minus 0 squared plus y minus 0 squared plus 0 minus z prime squared to the 1/2. Yes? I think. Okay, yeah.
Maybe dz prime.
dz prime. Yeah, so write it all out. It's a plus b z prime dz prime. 0 to L. And then the electric field is the gradient of that. Now, but it turns out that x, let's say the way that we choose the problem, we could have said, now in this particular case, I chose it at this point here, it's x equal to L over 2.
Yeah, that's what I was thinking.
All right, there's a 0 there. That is what you've got to solve for. Okay, that's relatively easy to look up. Yes.
How much weight will be given to the actual solutions as opposed to setting up the integrals?
I can't say exactly, but I'd say recognizing the right path to the solution. So here, for example, if you decided to write down Laplace's equation and attempt to solve it in Cartesian coordinates, and
Do selling.
well, okay, if at that point, then you actually wrote the boundary conditions properly along that line of charge, which involved delta functions, right? If you did that, then you'd be on a path that could lead to the solution, but most people would have trouble writing the boundary conditions. So that's not a viable path. It's not physically incorrect, but it's not viable. So if you carried that out in a reasonable way, but then stalled, you might get 3 or 4 out of 10, right? Whereas if you recognize that this is a problem that could be solved either by the potential or the field, you know, to take by actually integrating the charge distribution, because you were given the charge distribution, that probably recognizing that that's the approach and writing down the general integral to start out with, that's 4, right? Then realizing that it's going to simplify like that, that's probably another 2. Then looking up the integral correctly, and then recognizing that you have to take the gradient, that might be another 1. So I'm talking about 7 or 8 points for setting it up, getting it all, you know, just sort of simplified to the point where you could solve it, and then if you screwed up looking up the integral, that you lose sort of maximum 2 to 3 points. But to be honest, I actually just sort of gestalted, you know, and said, looks good, whatever. Yeah.
I get the coordinates confused. Are the prime coordinates for the
Prime
location of the
coordinate is
charge?
where the charge
Where
is.
the charge is.
Yeah. So this point that we're solving for here, the way that I've just written it, is at L over 2, 0, 0. All right, so that's where the L over 2 came in here, and then the 0 showed up over there. And if you wanted to do it by the field approach, this would end up being to the 3/2, and then I'd have z minus, or 0, I would have actually minus z prime. Okay, there.
That would be E equals the integral from 0 to L of that stuff. Right?
Well, that's just the z component. We'd have we'd have an x component as well. Which isn't so bad. No, the x component, so that would be easy. The x component would be the same integral a plus b z prime L over 2 minus L over 2 dz prime. Same thing on the bottom. 3/2. I think.
Wouldn't it be, why isn't it x minus
Where? Here?
Yeah.
I don't know. Here's what I wanted to do. I knew that the electric field had to point down. Oh, I took that direction. Yes. If this is plus x, then I stuck a minus sign in there because I wanted it to point down. But the way that I chose my axes here was that it was plus x in that direction. So you're right. You wouldn't have lost any points for doing that. So that was a problem on last year's exam. Problem 1, 2, 3, 4. So where are they? Those are the multiple choices. Here we go. Line of charge. Okay. Here's another problem from the examination. Consider a very long cylindrical tube of radius r.
Infinite.
The potential on the surface is given by 2 cos phi. I guess I should write that as theta, huh?
Which dimensional is this now?
I don't care.
Just write it down.
Oh, but not that one. The potential is that. Find the potential inside and outside of that tube surface.
Is that a sine squared theta or a sine 2 theta?
That's a sine 2 theta. Yeah. All right. So, what would you have to do
Boss's
there?
equation.
You'd actually realize that in cylindrical coordinates, the solutions are in sines and cosines, right? And so you've just basically got some r to the L. I'm just making this up. You should make sure that you got it right. R to the L, A sub L, cosine alpha, actually, yeah, I'll leave it like that. Alpha sub L theta plus B sub L sine alpha sub L theta plus r to the minus L solutions. So I probably have screwed that up, right? But that gives you the basic idea that the solutions are going to be sines and cosines azimuthally, and I think they really are just powers in R.
Radially.
Minus L minus 1. Or
Whatever.
Is there a 1 in there?
Minus
Yeah.
L plus
Okay,
1.
You look it up and you make sure, right? And then On the inside, these solutions will apply. On the outside, those solutions will apply.
This
Yeah.
cylindrical, it might actually.
Yes. Right, so that problem where I've given, where I've given you the potential on the surface, right? One thing that you can do right away, if you like, is determine what the potential at the center must be by averaging over the surface. And because those are sine and cosine functions, you know that it's going to be average 0 at the center. So you've got one boundary condition, the potential 0 at the center. You got another one, which is the potential goes to 0 at infinity, right? And then, you've got this one, the potential at that surface itself. Okay? So actually, it's overdetermined at this point.
Which is good
But you-
because
you
a
can
lot of
just
the
write
things
this
are going to be
down.
eliminated.
What?
Which is good because a lot of the
Yeah,
answers are going to be
we just
eliminated.
end up canceling out terms.
There's a lot of zeros.
And so it'll turn out, by the way, for this thing here, that the r to the 2 term, b sub 2 survives, let's say, and r to the 1 survives, a sub 1 survives. Okay, that's it. You don't have to do the whole set of integrals. You just recognize that your expansion was in sines and cosines, and then you just pick out the terms that correspond to what your potential at the surface had to be. Okay? So that was problem 3 on the examination.
And this is all going to be online.
So, as you can see, there was one problem that dealt with recognizing superposition.
Oh, thank you, sir.
One problem that dealt with recognizing the general form to Laplace's equation and then applying it with boundary conditions. One problem that I can't actually remember, where you actually have to do the integral of the charge distribution in order to find the potential in the field. So sort of one of each of those kinds of problems. And sort of oddly, Gauss's law was missed. Oh, there was a multiple choice problem on Gauss's law. And then problem 4, 1, 2, here we go, was an image problem. Yes,
Let me, I just didn't mention this, I've got anything on dipoles,
say that again.
on dipoles.
Here's the way that I think about that. That being able to recognize when a charge distribution can be expressed as a dipole, outside of a certain radius, can allow you to simplify
Okay.
a problem. Right? So I could give you a charge distribution and ask you to find the dipole moment of that charge distribution. That would be
So,
fair.
and is that also going to be something on that expansion thing that we get from
Nothing beyond a quadrupole,
Okay.
but the first multiple choice question on the previous examination was this. 4 charges are arranged on the corners of a square,
That's convenient.
like so. All right? At large distances r compared to the size of the square, the magnitude of the electric potential falls like
One over
Wait, say that again?
U.
V
No, that's
of
the
r
electric.
at great distance
Great.
goes like
I think that's the electric field.
r to the minus 1, r to the minus 2,
He says the
r to the
potential.
minus 3, r, and r to the minus 4.
Yeah,
Which of
it's R
those?
minus three.
For the potential. That's a quadrupole.
It's R minus three.
So it's the next one down. I'm going to leave that to you to argue amongst yourselves.
I'm not-
And I was going to do another example on
The talk cancels one.
Not an example. I was going to actually do a little bit of new material, but I'm not. Okay, so then I brought along my solutions to the homework in case anybody has any quick questions. And then, of course, tomorrow I will be available. Oh, let me make a couple of comments on the homework that's
Yeah,
due
impulse is one of our.
Thursday. And unfortunately, I printed it in normal size print.
Where our promise.
So I need glasses.
Yeah, but that's because these are all squared.
Let's see.
These are R squared, and those are R to the fifth.
Homework 5. Find the potential and electric field produced by a uniformly polarized neutral sphere. I did that in class and just posted the solution today. So the notes have got it fully solved out. A thick spherical shell of inner radius A and outer radius B is made of dielectric material with frozen in polarization. So it looks like this. How many of you have started the homework?
I finished.
Okay, good. How many of you have finished it? Usual suspects.
So whose cars are Sozer?
That's a good movie, by the way.
Who's what?
The Usual Suspects.
Okay.
It's Butler and Meg, right?
Thank you. Okay.
You'd only know that that's irrelevant if you'd actually watched the movie. Therefore,
Thick
it's
spherical
objectively
shell has
invalid.
got polarization that looks like this. P is equal to K over R hat. There is no free charge. Find the electric field in all three regions using the following two methods. All right? I'm actually, so this material's got dielectric constant epsilon, and there's nothing anywhere else. And I'm going to do part B right out for you.
I know.
I'm just going to go ahead and do it for you. All right? There is no free charge. You know what that means? The T field everywhere is 0. But wait. D is equal to E plus
7 lines.
4 pi p.
Once I
What does
figured out
that tell
what
you
to
the
do.
E field must be?
Negative 4 pi.
Okay, I'm not going to go any further with that. The first part of this problem, where he asks you to do it using Gauss's law, is harder.
Yeah.
All right?
It's kind of irritating.
You actually have to do, you're going to have to write down that E times 4 pi r squared for a Gaussian surfacing here like that is equal to, well, where am I? Oh, no, first we have to do this. Sorry. Before you get, oh, well, okay, I'll write this, is equal to, I can never remember whether there's a 4 pi here or not. I'll put a 4 pi here.
There is.
4 pi charge enclosed. It's all charge enclosed, all right? Rho bound is equal to divergence of P with some 4 pi or not, maybe minus sign or not. And sigma bound is equal to P dot N at the surfaces. It will turn out that there's surface charge at the inside surface and the outside surface, and there's a bound charge throughout. Okay? Then once you've got these two things, you can go back to that and find out what the charge enclosed is. It's messy, but not too bad. On the other hand, T is 0, so E is minus 4 pi p. Done. Yes.
Why do you use B there? For
Bound.
Oh,
Bound.
bound.
What's wrong? But didn't you say you dislike that notation?
I do.
But Ohanian uses B.
He uses P
As sub P is in C.
for polarization.
Who cares?
Whatever. I'm using bound
P for bound.
and free. Right, P for bound. Okay, that was that one. Ohanian problem, 4.0 for the difference between two dielectric electric field in the first. Let me just comment on that one, problem 20. where you have a slab of dielectric sitting in an external electric field which sort of points at an angle through the surface. The answer is going to come out messy. It's going to have cosines and sines and epsilon 1s and epsilon 2s. It's messy.
Got cotangents too.
Okay. Well, you could rearrange it in order to make cotangents or tangents
Yes.
and cosines or sines on the outside of the equation. All right, so I'm just telling you that it's messy. So don't get surprised if it looks messy. And then problem 21, space between the plates. I did that in class with a single dielectric, and I'm not going to help you to do two dielectrics. Remember that the D field doesn't care whether there are dielectrics in there or not. So solving for the D field is really easy once you're given the charge density on the surface, which you are. Okay, any comments or questions? Calvin and then Ryan.
Can you go over the difference between down charge and free charge? Can you just define them again? First, so that there's a distinction.
I'm just trying to come up with a different phrasing here. Bound charge is what arises from the polarization of a dielectric. So you look for those key words in there. Right? Free charge will be either the net charge on an object, so we say we added this charge to it, or charge that's, and this is a little, this is troublesome, right? Charge that's in a metal, all right? And that's, even though you could view the metal as just polarizing, it polarizes infinitely well, and dielectric function is the zero field dielectric function is infinite, right? The way that we think about it is that the charge in the metal is free to move macroscopic distances, and the charge in a dielectric only moves of order an atomic distance. So you look for the key phrases: polarization, bound, and that's pretty much it. In order to identify something as having either just bound charge, and then you look for added charge, net charge, or the charge in the metal in order to think about free charge.
There, for problem 3, Wikipedia, Shelms doesn't have the identity, oddly enough, but Wikipedia, under list of trig identities, has a list of trig identities of like cosine, of like, say, cosine of the inverse, of the arc cotangent.
Oh.
That makes it much simpler. And
You mean it allows you to simplify the final expression?
yeah, it makes it look much nicer.
Yeah, okay, it's prettier. Good. But I'm okay if it comes out to be messy. You've still done it right. You've just done it better if it's neatly reduced. Brian?
I would also like to wonder whether we're assuming the surface charge has, or that there's any surface free charge or not.
Oh, if I don't tell you that there's surface free charge, there's no surface free charge. I have to tell you. Yeah,
Specific question,
There we go.
number, 4.04 out of 1.
yeah.
Until specified.
Draw it.